So we can start. Let's record the video first. Okay. Okay, so for today's is the first session for advanced computer architecture course. This is actually the course which is continued from the previous course from your year 3. So I hope you still remember what you have done so far in last year. And for this course, we are going to work on some of the technology behind how computer organize itself, how it execute the program, and especially we are going to practice with the design a new architecture for ourselves. So in this course, we have 32 hours, which is 16 sessions. And there are a lot of topics which we present later. And what is important is that we are going to practice with the design CPU. Actually, this is something that the topic I introduced this year. And so we will see how if it is too hard or not, because we need to do a lot of simulation. Anyway, for this hour for the session, I'm not going to go deeply into the course yet, but we will start with some introduction and the review from the previous year. Because it's important to remember, to understand what we have learned so far before we can continue from here. The slide presentation, I already placed it in the course material here. So you can come into the class material and then presentation, and you can download it to view by yourself. So let's get started. Okay, so just a definition. What is computer? Just a computer, in a short definition, is an electrical device which can input data, it can process data, store data, and output data. So any device which have this functionality can be considered a computer. For example, a calculator can be also considered as a mini computer because we can input a number inside with the keyboard. We can display in the screen. It can process data, kind of simple arithmetic operation, and also it can sell some data as well. So the calculator can be considered as a mini computer as well. A smartphone will be as a computer as well. It's just that it has some more unique feature. That's why they provide another name for it, like calculator. Especially, its special feature is about calculate number. Smartphone is special number. A special feature is about communication and maybe taking photos, something like that. So that's why they use the different name. But actually, any electrical device that can that have all these features can be considered a computer. In the computer, we talk about the component. We have the CPU. We have the memory. When I talk about memory here, it doesn't mean that I refer to only RAM, but also any memory unit inside the computer. So maybe you still remember about the memory unit. We haven't gone so deep inside, but at least we know what are the components that can be considered as a memory. For example, we have the RAM, ROM, we have hard disk, we have register, we have cache. Yes, and they are all called a memory unit. And then we have some device like GPU, and maybe here hard disk and many more. So I just pick a few to show it what are the components inside a computer. But they are grouping all together to form a motherboard. The motherboard is an integrated circuit that connect all the devices together to form another component which is called a computer. Right? Just something for review. And here is the schema about what is inside a computer. So we have here, you can see the input unit. We have the storage unit, or maybe you can call it memory unit, the same thing. And we have the output unit, and then control unit and arithmetic logic unit is the component inside a central processing unit, and it communicates with the storage unit to process the data. Right? So what is central processing unit? Central processing unit, which is commonly known as a CPU, it's a electronic circuit that is used to do some arithmetic and logic operation. So the arithmetic operation can be as addition, subtraction, multiplication, division. They are all the basic arithmetic operation, and also it can also process the logic operation such as AND, operation AND, operation OR, XOR, NOT, something like that. And when it combined together, it can process a very more complicated operation. In any case, the CPU is the brain of computer, which is used to operate the data. Inside the CPU, we can have the ALU, we have the CU, we have the register, and we have the CPU bus. So the CPU itself is composed of multiple other components. ALU, which is coming from the whole word, is arithmetic and logic unit. CU is a control unit. And register, we have a lot of register in CPU. We have like instruction register, memory address register, program counter, memory data register, and so on. It also depends on the architecture of the CPU. So some CPU may have a lot of register, some CPU may have only a few register, but it depends on its architecture. For this semester, we are going to go deep with the CPU design. So we will practice a lot with it. So you will see the structure later in more detail. And then we have the memory unit here. Memory unit in the last year, we haven't go deep inside. We only talk about the general description. What are the memory we are using? What is RAM? What is ROM? Just something like that. But for this semester, we are going to go deep inside how memory is organized data, how it can be accessed from the CPU, and what happens if data is not found, what happens if data is found. So we will talk about this a lot in this semester. So now you can just remember that what are the components that can be considered as memory unit. The first one is about register. So register is the fastest and smallest memory unit inside computer. It's just that register, there are many types of register. Like I said before, we have IO, we have MAO. AO, MDO, I forgot to change this. Actually, this one is MDO. And we have accumulator and so on. So there are many more register. And register are the memory unit which is located inside a CPU. All right. So it used to each register have their own functionality. For example, the IO here, it is used to store the instruction. So when one instruction is transferred from the main memory, it will be stored first inside the instruction register. before it is being decoded and executed. So IO is something that's stored in the instruction. We have AO. AO is coming from the word memory address register. Is the register we use to store the address of the next instruction that we need to copy from RAM, and also maybe address of the data that we need to transfer from RAM. And for MDO, maybe I should change it first. MDO. Yeah, MDO is a memory data register. It's the register which is used to store the value coming from the main memory. So MAO and MDO are working together. MAO is store the address before copy from RAM to the CPU. MDO is a register which store the data that copy from RAM. Okay. And I think you still remember, right, the video that I played during the last year about how a CPU works. It's a bit complicated, but the flow is exactly like this. Go to MAO first to plan the address, and then copy to MDO, and finally, if it is a register, it will copy direct to the IO. All right. If you forgot about it, maybe you can go back to the video that I shared before. I can also say it again in case you forget, because it's actually quite a good video showing how the CPU works. And then we have the accumulator here. Accumulator here, it doesn't present in every CPU architecture. In some general purpose CPU, it always have the accumulator, but in some architecture, it doesn't have it. So what you can see in my presentation here, it doesn't mean that it will present in any other CPU. So it's just an example. And we have many more registers. Right, and then after register, we have the cache. The cache is also considered as a memory unit. The cache is a bit bigger than the register, a bit slower than register, because the cache sometimes is not located inside CPU. It will close. Cache is close to CPU, and sometimes some level of cache is located inside the CPU, but mostly cache can be inside CPU and close to CPU. So the speed is a bit slower, and the size itself is a bit bigger than register. Okay, if you have question, you can ask me. You don't need to wait until I finish talking, because if not, I just keep talking like that. So it might be too fast. Cache have a lot of type. Actually, there are many more than this. Just this, we talk about it a lot. In cache, you can have L1, L2, and L3. So when you are browsing computer store to buy a new computer, I think that you will see about the specification. They are talking like the cache L1 is 2 megabytes, 3 megabytes, like that. So cache is something that used to improve the performance of a computer. So we have different type of cache here, L1, L2, and L3. And then we have TLB. TLB is also a cache, but it's a cache of a page table. Maybe you don't know about it yet, but you will see it soon. Anyway, TLB is also a cache. All right. Just a cache, but it located like L1 is located on the CPU, inside the CPU. R2 is maybe inside or maybe on the motherboard, but close to CPU, and L3 normally is located inside the motherboard. But anyway, they are very close to CPU. They are used to improve the performance of the program, because cache is something that store the frequently use data or maybe frequently use instruction so that it can improve the performance of the program. And then we have the primary memory. The primary memory here we have like RAM and ROM. RAM is a random access memory. It is a volatile memory that store data only when there is electricity. And for ROM, it's a read-only memory which store data permanently. And there are a lot more. If we talk about RAM, because there are different types of RAM as well. We have the SRAM, we have the DRAM, and inside the DRAM, there are many more types like SD3, SD4, and now the latest version it should be SD5. No, sorry, DDR3, DDR4, DDR5. But they actually an SD memory. Okay, so there are a lot of memory or RAM inside in our computer, and anyway, they are called primary memory. Okay, and then we have secondary memory here. We have the SD, we have the magnetic disk, and then we have the external memory like USB flash, CD. Right, so all these components are considered a memory unit. It have their own functionality, but what is the same is they are used to store data. Right. So after that, we are talking about the input-output unit. Input-output unit, normally you can just call it peripheral. It's some the external device that connect together with the computer. But normally inside a computer, there is a module called input-output module, with is used as a middleware between the external device and the computer inside. Okay, and for input-output module, we haven't learned about it, so I just skip it. I just introduce about input and output unit, which is the external device such as a keyboard, mouse, microphone, or maybe output unit can be like monitor, printers. Okay, so it's important for input-output unit. And then what you have learned from the beginning until now is just the first phase about computer introduction. Just to remind you about what we have learned, what are the components inside. And also, actually, I forgot to mention about the generation of the computer. Up until now, we have 5 generations. The first generation is about the vacuum tube. Maybe you still remember, right? A vacuum tube is something that's very big device that used to operate inside a computer, which is later replaced by the transistor, because transistor is a lot smaller and more powerful. And then we have the integrated circuit, which is introduced in the 3rd generation. And then we have the microprocessor in the 4th generation. And until now, we talk about the software, which is focused in the 5th generation. And currently, we are in the 5th generation of the computer. So here, for this presentation, for this slide presentation, we are focused on the software, how it is organized itself, and how it is transferred into CPU to be executed. Any questions so far? I will pause a bit for you to look for questions. Okay. All right, maybe there are no question. We can continue. And then here we talk about the software, the program. Program is the series of code that is written and then stored in the secondary memory. And when it required to it needs to first to the main memory, the RAM. All right. So program is the combination of instruction. It is a series of instruction. We have 1, 2, 3, 4, and many more. And then it's also combination of data. So inside a program, there are instruction and data. Data can be integer, can be string, can be Boolean, can be number, whatever. So we just call it data. And instruction, there are different type of instruction as well. So instruction, actually, it have its own architecture, and what we call it is instruction set architecture. So instruction is a combination of operation code and the operand. There are many types of operation code, and the operation code is different between the architecture of the CPU. So when you design a CPU, you need to also think about the instruction. If you want to have a very complicated instruction, you need to have a device support it, as well as if you want to have less instruction, you also need to have the component fit with that kind of instruction. So normally when you design a CPU, it's coming together with the designing of the instruction. In any case, instruction is always composed of two sections, which is opcode and the operand. Some instruction may have only opcode. Some instruction may have one operand, and some instruction may have 2, 3, and more operand. It depends on how you design it. The operation code can be something like load, add, sub. Yes, a lot. You can think about what we have learned in the assembly language last year. So,
phảiធ្វើបែបគាត់បើគេលុយគេដាក់ឲ្យកន្លែងហ្នឹងហ្មងហ្នឹងទៅ
okay, maybe not a question, I guess. And then when we want to execute the program, we need to transfer the instruction one by one into the control unit, into the CPU, which is stored in the instruction register. Okay. So the default behavior of executing a program is by transfer one instruction after another, and normally it goes by sequence in order from top to bottom. But you can run the brain instruction, which can change the order or maybe skip some instruction. Right? Remember in the assembly. And when you transfer the instruction to the CPU, after being decoded, it means that CPU can know what kind of instruction it is. Maybe the instruction to transfer data from memory to the another component, or maybe the instruction to do some arithmetic operation. So after being decoded, the CPU can understand what kind of the instruction is. And in case that the instruction required to transfer data from memory, you need to call the access memory operation. And the access memory operation here, normally we need to use the bus. Inside the computer, there are 3 kinds of bus. A bus is like a electronic circuit that you can transfer data from one component to another component. And in the bus, there are 3 kinds of bus. One is the data bus, and then we have address bus, and finally we have a comment bus. All right. So when you want to communicate between components, especially in our case, get data from the main memory. So you need to send the address first through the address bus, and then send the signal read through the command bus, and finally memory will transfer data back to the CPU through data bus. All right. But when we talk about transferring data from RAM, it's not just about how you transfer it through which circuit, but also the way that you read data from memory. In the computer architecture, there are different kinds of addressing mode. Addressing mode here is a mechanism to differentiate how you can access data from main memory. Or in another word, it's about how you can locate the effective address of the data you want. So here we have different kind of the addressing mode. We have the immediate addressing, we have the direct addressing, we have the indirect addressing, register direct address, register indirect address, and then we have the replacement addressing mode. Remember? So we will do some little practice about this addressing mode. I hope you still remember it. So after this presentation, we will do some exercise here. And also, we have the ebook. I think I haven't uploaded here. Because for this lesson, we still use some material from the previous ebook. I will upload the ebook here. In case you haven't download before, wait a bit. This tool. Okay. All right, so we are going to use two ebooks together. For last year, we talked a lot about this ebook in here. For this semester, we still use some chapter from here, but also we also use some chapter from here. So you better read this two ebook. For now, we are going to look into this ebook. You can download it from the class material, and then we can look in it together. Okay. Actually, this is a very good ebook about computer architecture. I hope you have read a lot about it already. And inside, there is a section about talking about the addressing mode. Addressing mode. Here it's this. Here in chapter 5, page 212. 212. So just go through the ebook together. We are going to practice a bit about the addressing mode. Here's the address 212. 212. Yes, here. So in here we are talking about the addressing mode, and there are different kind of addressing mode here. All right. We already talked about it in last year, so just to review so that you can remember. We have immediate addressing, we have direct addressing, we have registered addressing, or you can call it registered direct addressing, which is the same thing. And we have register indirect addressing, and then we have index and base addressing. Sometimes they call index addressing mode as a displacement, so they are the same thing. Displacement addressing mode or index addressing mode, the same thing. And there are more like a state addressing, and there are a lot more here. All right. So we are going to practice a bit here. Let's imagine with this scenario, the structure of the memory. Here is our main memory, which is the RAM. And the number at the front is called address. The content inside is called data. So remember, the memory is the combination of address and data. And what you see here, there is the register of one. Register of one here is just something that they name it like that. It can be or one or two or three, just what you name it. And in here, in the example, they provide that at address 800, the number or the data is 900. The address 900, the data is 1000. The address 1000, data is 500. So see, this is just some assumption, some data that they provide to you. So for practice. So imagine that you are executing the instruction load 800. What is the difference if the addressing mode is immediate, if the addressing mode is direct, if the addressing mode is indirect, and if the addressing mode is index? All right. So if we are talking about the immediate, load 800, the number 800 here is the operand, and the operand here is the value itself. So if it is the immediate addressing mode, the load 800 we will move the 800 here into the accumulator directly. Instruction load here, I forgot to mention that load is an instruction which is used to transfer a value to accumulator. And you see here, AC refer to the accumulator. So if it is the load 800 and it is an immediate addressing mode, it means that we are moving the value 800 into the accumulator directly, right? If it is the direct addressing mode, it means that 800 here is the effective address. And the effective address is the address of the data that CPU wants. So make sure you understand what is effective address. So if it is the direct addressing mode, 800 here is the effective address. And if it is effective address, you need to locate it inside the RAM. Here, 800 is the effective address. That means that when you run the instruction load 800, the value that will be copied to accumulator is the value 900. That's why if in the direct addressing mode, you will have 900 inside the accumulator. All right? Any question? And if it is the indirect addressing mode, it means that the 800 here is the address of the effective address. So to get the real data inside the accumulator, what you need to do first is to find the effective address. So 800 is the address of the effective address. So you go to RAM, you can see that 800 here, and you know that 900 is the effective address. That means that you need to copy the value 1000 here into the accumulator. All right, that's why if it is indirect addressing mode, you will have the value 1000 inside the accumulator. Okay. And finally, if it is the indirect addressing mode, it means that 800 here. To get the effective address, you need to use this 800 here in addition with the value of register of 1. All right. So 800 and 800 is 1600, and that combination becomes the effective address. And you go back to RAM, you will find the value 700 here. That's why you will get the value 700 in accumulator in case the addressing mode is index addressing. All right, it's a bit complicated, but if you have done it a lot, you will get to understand how easy it is. Just remember the formula: immediate, direct, indirect, and indirect. So, question? No? Here you can find the more explanation inside this table, the table 5.2. It's tell how to find the operand. You see, with immediate, the operand value present in the instruction. If it is direct, effective address operand is in address field. If register, operand value located in register. Okay, so that's what I told you before. So you can find more detail, more description inside this table. All right. So coming back here, actually, I already told you in the slide presentation. It's just that I haven't mentioned the detail about when you copy instruction into the CPU, what happened. Okay. So I skipped the section how or what happened after you copy the instruction into the CPU. So the process is that when you feed the instruction inside the CPU, you need to copy it into the instruction register. Later, I will show you the video how it is worked in more detail. Just for now, I will explain a bit what are the process when you copy one instruction into the CPU. What happens next? The first step is the feed instruction, and in this step, it will copy the instruction from memory inside the I/O register, and then it decode the operation code to make sure that CPU understand what kind of operation code it is executing. Maybe it's an instruction load, maybe instruction addition, or maybe subtraction, depend on the operation code. And then it calculates the effective address based on the addressing mode that I told you before. And then we need to fix the operand in case the instruction require operand. If it's not, you can skip this step. But if it requires some operand, you need to fix the operand. And then we need to execute instruction, and finally we store the result. Okay. So actually, you can group them into three steps: fix, decode, and execute. But if you want to have more detail, you can split it into more steps. Like here, we have 6 steps. All right, so it's explained a lot how it works here. And by the way, to your question now, you can ask in Khmer as well. Maybe I explain in Khmer and also in English. In the meantime, I will find the video that you can look through it first. I think it's a good video. Wait a bit. Yes, and this is the video. I hope you still remember. I copy the link here. You can see it in chat. Okay. So maybe we will look into this video together. Do you hear the video sound? Hello? ពួកយើងលើសលេងវីដេអូអត់
អត់
អត់លើទេ
លើតែបើកម្ដងទៀត
លើអត់
អត់លើ
អត់
Ủa, họ share một sao
ចូលខ្ញុំ share ម្ដងទៀត
There are lots of different wires carrying
លើអត់លើ
yes yeah.
Okay, so we will look into this video together. I think you already see this video before, just for again, because it's important to understand how CPU works.
The CPU, short for Central Processing Unit, is like the brain of the computer, and once you understand how it works, you'll understand the computer as well. Let's remove the cover of the CPU and zoom in to see what happens inside. There are lots of different wires carrying information around the CPU. This particular CPU is called the 6502 and was used in computers like the Apple II and the Commodore 64, as well as in the original Nintendo Entertainment System. This simulation of the 6502 can be found online at visual6502.org. In every CPU, there is a particular wire that turns on and off at a steady rate to help keep everything in sync. That wire is called the clock, and the clock in this simulation is turning on about twice a second. Modern CPUs are measured in gigahertz, giga meaning billion and hertz meaning times per second. So the clock in modern CPUs turns on several billion times per second. That speed is what allows CPUs to do very complicated things very quickly. However, what the CPU does during each clock tick is actually very simple and something we'll look at more in this video. For now, we'll zoom back out and put the cover back on. The CPU in your computer might be manufactured by a company like Intel or AMD, but the type of CPU we're going to look at today is called the Scott CPU. The Scott CPU doesn't actually exist except as a design in a book called But How Do It Know by John Scott. The design of the Scott CPU is copyrighted and is being used in this video with John's permission. The book is available at buthowdoitknow.com. This is a great book that goes through each of the components in the CPU very slowly, without using a lot of overly technical jargon. If you've been looking for a book that explains how a computer works, I would highly recommend this one. So let's flip the CPU over and look underneath. You'll see a lot of pins sticking out that allow the CPU to take in information and send it back out. The CPU fits into what's known as the motherboard. The motherboard allows all the components in the computer to connect to each other. So we'll flip the CPU back over and plug it into the motherboard. On the right of the motherboard is a place for something called RAM. RAM is short for Random Access Memory, and it just contains all the data that is being processed by the CPU. Let's learn a little bit more about RAM by looking at how the CPU and RAM interact. For now, we'll remove the wires on the left and move the motherboard over to make room for the RAM chip. RAM consists of a list of addresses, and at each of those addresses is a piece of data. The CPU normally requests and processes each piece of data from RAM in order, one after the other. However, if the CPU is instructed to pull data out of order, it can do so. That is why it's called Random Access Memory. The data can be accessed randomly if it needs to be, although normally it's accessed in order. When the computer first starts running a program, it sends an address to RAM to begin retrieving that program. The RAM address just consists of a series of ones and zeros representing on and off wires. RAM doesn't do anything with that address though until the CPU also turns on the set or the enable wire. If the enable wire is turned on, RAM automatically sends whatever piece of data is at that address back to the CPU. That data is then processed by the CPU accordingly. Once the CPU is finished processing that piece of data, it then sends another address to RAM, turns on the enable wire, and gets the next piece of data from RAM. This process happens over and over again inside the computer. If the CPU needs to save data to RAM, it outputs an address outputs some data, and then turns on the set wire. The RAM will then overwrite the data at that address with the new data. But what is that data inside RAM? Because it just looks like a bunch of ones and zeros. Well, it's made up of different things. Some of the most important pieces of data in RAM are the instructions. Instructions just tell the CPU to do different things. There are also numbers inside that data. These are numbers that you might want to add together, compare, or simply process in some way. Another thing, and this is kind of weird, that is in the data is addresses. At particular memory addresses in RAM, the data itself is also an address. These addresses can be used for various things. For instance, if you want to output a number to an external device, you have to know the address of that particular device. Do you want to send data to the printer, or do you want to send it to the monitor, for instance? There are also letters stored in RAM. If you want to show some text on the screen, you would actually store it as a bunch of ones and zeros in RAM. Each letter is stored as a particular combination of ones and zeros according to a character code. These character codes are arbitrary. Someone just decided that this is a lowercase a, and this is an uppercase G, for instance. So that's what's actually in the data inside RAM. Now let's go back to seeing the data as just a bunch of ones and zeros. And we'll now move the RAM chip into the RAM socket on the motherboard. We'll then group the RAM addresses and data together, pull the CPU out of the motherboard, and look at what's called the instruction set of the CPU. As we saw earlier, some of the pieces of data in RAM are instructions, and each CPU has its own set of instructions that it understands. So there might be a load instruction, which loads a number from RAM into the CPU. After a couple of these load instructions, there might be an add instruction that adds these two numbers together. After an add instruction might be a store instruction, which saves the result of that addition back out to RAM to be used later on. There might also be a compare instruction after some load instructions, which compares two numbers together to see which one is larger or if they are the same. The compare instruction can be very useful when used in conjunction with what's called a jump if instruction. As we saw earlier, the CPU generally requests each piece of data from RAM in order one after the other. Sometimes, though, the programmer wants to jump to an out-of-order RAM address to process some other instructions in memory. The jump if instruction checks to see if a certain condition is true before it jumps. It uses the results of the compare instruction to make this decision. There is also a regular jump instruction that jumps no matter what. Finally, there is an out instruction and an in instruction. These will output data to an external device like a monitor or input data from an external device like a keyboard. These two instructions are often used in conjunction with an address, like we talked about earlier. There are some other instructions in a CPU's instruction set, but these are some of the more commonly seen ones. So as we saw, the data in RAM consists of things like instructions, numbers, addresses, and letters. So let's go through a program that would use this instruction set to play a guessing game. So it would load a number like 9 into the CPU. Let's say that the programmer decided that that was the right answer, so he went ahead and put that number into RAM. And then comes an in instruction to retrieve the user's guess. After the in instruction is the address of the keyboard, so we can know where we're getting the data from. Next comes a compare instruction that checks to see if those two numbers, the one saved by the programmer and the one entered by the user, are the same. Following the compare instruction is a jump if equal instruction, which will jump to another address in RAM if those two numbers we just talked about are the same. The jump if equal instruction is immediately followed by a new RAM address. If the two numbers are the same, the CPU jumps to that new address to begin processing its next set of instructions from there. If the two numbers are not the same, then the computer ignores the jump if equal instruction and the corresponding address and just keeps going. Following the jump to address comes an out instruction with the address for the monitor, then the letter capital G, and then below that would be the letters U, E, S, S, space again, so guess again. So if the user guesses the wrong number, the program would tell him to guess again, and then jump back up to the in instruction to retrieve that new guess, and then process these instructions all over again. By the way, the in and out instructions used here have been simplified somewhat, but you'll find them covered in more detail in the book. So now let's briefly take a look inside the CPU itself to see how it would process an instruction. As we saw earlier, this is the inside of the 6502 CPU. Let's take away the 6502 wiring and see what's inside the Scott CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the two inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare
Cú chụp lư thì đấy.
Mấy con lưới rồi, lưới từ đây. Lố.
Ọt lư một đường tí ngủ. Một đường lư rồi.
Lưới lưới rồi.
Ọt lư không? Mà mới tôi lên lư rồi.
Chừng ngọn lưới vô nữa chứ.
Mình là cứ tầm mình.
Cái lụa lưới tăng bị tao mà xem một tiền bây giờ.
Ọt em muốn lư đó.
it.
Lừa lại.
In this case, it's the jump if equal instruction, which to see if the equal flag is on. It does that by running one of its wires at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU and put it back in the motherboard. Using the ports on the left, we can now plug in the cables that connect our monitor and our keyboard. Each of these ports has an address, and that port address is what the CPU uses with an in or an out instruction. That port address, by the way, is sent using the data bus, since the address bus in this computer is only used for RAM. So we'll zoom out to see how the motherboard fits inside the computer case. In the computer case is the last component we'll look at, which is the hard drive. As soon as the power to the computer is turned off, all the data in RAM is lost, so you have to have a way to store it more permanently. For that, we use a hard drive. Inside the hard drive is a spinning disk covered in tiny magnets with a small metal arm floating above it. The arm moves around to the different parts of the disk where different data can be stored and retrieved. The disk and the arm generally move very, very quickly, but nowhere near as fast as the CPU can process data. For this reason, all the data from the hard drive must first be moved to RAM before it can be processed. So we'll put the hard drive back inside the computer and zoom out. Here we can see the program we just ran and the message telling the user that he guessed correctly. So now you've seen the very basics of how a computer processes information. You'll find much more about the Scott CPU and the book at the website buthowdoitknow.com. Also, there are a few small differences between the book and the video, but those shouldn't detract from your understanding of either. You can find a list of these differences in the video description. Thanks for watching.
Okay.ចាំបានអីគេខ្លះ ចឹងវីដេអូតាមពិតយើងរៀនតាំងពីឆ្នាំទៅ Okay, so it's a bit long video. It's about 20-minute video, and it explains a lot about how the CPU executes the data, and especially how the circuit and each component work together. It's if you don't really understand about it, because I believe so, it's quite a long video, and I recommend for you to look into it again a few more times maybe. And I see also the problem with the subtitle, and it's quite in the wrong timing. So it's better maybe just listen to it, I think. Any questions so far from the lesson I taught in, or maybe what you see in the video that you think that almost understand but need some help? I can also help you. Any questions so far? No? No question? The addressing mode in the last slide presentation, I want to do some exercise, but I'm not sure it's necessary or not, because actually we have done it already, some about the addressing mode. Maybe let's just do it a little bit, just to remind you about addressing mode if you don't have question about the video, also the lesson. So we have two exercises only about the addressing mode. So just spend some time. Let's do this number 13 first. Number 13. If you have your ebook, on your computer, you can open it. If not, just look into this and see a little bit. The question here is just like what I told you before about how to locate the data inside the accumulator. So just do some practice a little bit. Okay, I will give you some time to think about it. Okay, so tell me the answer here. Anyone, what is the value in the accumulator in case it is the immediate decimal? Hello? Hello? Can I?
Yes.
Yeah. So what is the value of the accumulator here? If you don't know about the answer, you can look through what we seen a moment ago. And remember, it page 212. You can see in that page, give you some idea. Here, 215 is explain what is immediate, what is the right, what is the right. And here is the example. Actually, the same thing. It's the same thing. Okay, page 214. Yeah, 214, 215. And here Where is it? In here, yeah, 2.5. Explain how to get the value. Anyway, if you don't know, if you have to correct it for you. I think this exercise we have done it last year already.
Not sure.
Yes.
I think 200.
Here, 200. Are you
Yes.
sure? No, this one is not 200. This one is 1000. Do you get it? Why it's 1000? That
Oh, I
is,
see.
yeah,
Yes.
okay. Because the instruction is load 1000, and if it is the immediate addressing mode, the data is in the instruction directly, which means is 1000 is the data that we need to copy into accumulator. All right. It is something for the exercise, so let's do it together. For this case is, what is the value for this case? Now exercise number 14, actually the same with 13. It's just different number. What is the value here?
500.
500.
Yes, because it is immediate and the data is the operand itself. All right. So we come back to exercise 13 and then we do for the direct. So the direct here is what is its value here? Tell me.
1,400.
Yes, 1,400. Because if it is the direct addressing mode, the operand here is the effective address. Okay. So come back here. What is the value here? Direct. Anyone else?
100.
100. That's correct. And then coming back here, we have the indirect this time. And indirect here, what is the value?
1,300.
1,300. Yes. Because it is in the indirect, it means that 1,000 here is the address of effective address. So to get the value, you need to find the effective address first. 1,000 is contain the value 1,400, which means that 1,400 is the effective address. And then you need to get the real value by going to the address 1,400 and you get the value here. So the answer is 1,300. All right. So here, and someone else in the right here. Hello. 600. That's correct. All right. And finally, the index. When we talk the index, normally they need to mention which register you need to use. And here it's also mentioned that all one is implied in the index addressing mode. Okay. So in our case here, the index, to get the effective address, you need to do the addition between the operand here with the value of register. All right. So 1,000 with 200 is 1,200. That means that the value it need to get is 1,000. All right. In case of in the addressing mode, the effective address is the value of operand with the register. Okay. So this one, what is the value?
800.
800. We have 500 plus 200. All right, we get 700, and then the value is 800. Okay, this just something just to remind you again. about the addressing mode, because it will be useful later when you work on a simulator. You need to understand how addressing mode works. There are more than these 4 addressing mode, but this the 4 basic. So just make sure you understand about it, and especially understand what the addressing mode means. It's important. All right. So today I think we just focus on the review from previous year, and when we next week we are going to work on the memory organization, about how the data is stored inside the memory, about the connection between the register with the cache, with the main memory, and with the virtual memory. And after that, we are going to work on different architecture of the computer, like the parallel architecture, like there are many more architecture that we are going to work with. And finally, we are going to design our own CPU by using some simulator. Okay, I will provide some of the core material later, especially about the simulator, because you are going to look into it by yourself first. And especially, I think you already learned about the logic combinator lesson. I think that's from the year 3, right? It should, at least for you to understand about the logic gate, because we are going to need it. So today we will finish this. If you have, if you don't have question, but if you have, I will stay behind. And do you have any other question? No? All right. If not, good weekend.